Welcome back to ECE 442-542. In this presentation, what I would like to do is finish up our DC motor example controller design using the direct design method of Ragazzini. We've been given a normalized DC motor that has two poles, a pole at the origin and a pole at -1. Our design specs, we said let's just try for a percent overshoot of 5% and a settling time of 1 second. We use those design specifications to actually select a sample period, capital T, of 20 milliseconds or a sampling frequency of 50 hertz. We then found a zero order hold equivalent from that normalized DC motor using that particular sample period. And we can actually do that also within MATLAB. We could say that we now have our continuous time plant as a transfer function. And we can now find the discrete equivalent using the C to D function with that continuous time waveform and the sample period of 20 milliseconds. There is now our system. We could look at, if we didn't know what those were from inspection, we could say where are the zeros of that. We have one at a minus Z value on the real axis of minus 0.9934, and our poles are at 1 and 0.9802 on the positive real axis. There is now our system, capital G of Z. We now want to, in the approach of Ragazzini, we need to build this desired closed loop transfer function, capital T sub C of Z, and based on our G of Z, we realize that we need to have a pole zero excess in T sub C of Z of at least 1. We also can, from the earlier design specs of a percent overshoot of 5% and a settling time of 1 second, in our previous lecture we created, or we found, the dominant pole locations in the Z-plane corresponding to those design specifications, and they're almost two real poles, but we do have an angle of about 5 degrees, or a little bit more than 5 degrees. Maintaining our pole zero excess of 1, we have a numerator order of 1, we have a denominator order of 2 with the appropriate dominant poles in place. What we don't yet know are the K value and the alpha value, and we will select those or design those into T sub C of Z in order to satisfy our steady state air specifications. The steady state air specifications, which I will now state, we would like the steady state air to be 0 when we have the reference input as a unit ramp, and we also want the air to be 0 when somebody injects a reference signal of a constant. And so we're now wanting to use those requirements to specify alpha and K in our desired transfer function, capital T sub C of Z. A ramp input, R of Z, is now T times Z over Z minus 1 squared, and what we are going to find is that we can actually find alpha and K not independently, but separately, so that we can now select alpha based on the ramp steady state air spec, and we can select K in that order based on the steady state air due to a constant. The air expression, just as a reminder, in our standard block diagram with unity output feedback, we have E is now the difference between our reference input signal R and the output Y, and Y, because of its relationship with R, we know that this particular transfer function between the reference input R and the output Y is our desired closed-loop transfer function, capital T sub C of Z. That's why in blue now we can see that we can replace Y with T sub C of Z in our air equation. We can factor out the common R, and now we have an expression, or we will have an expression, using the final value theorem to try to drive that air as time marches to infinity. Using the final value theorem, we can now say that the limit as z goes to 1 of the quantity z minus 1 times E of z, we want to drive that, or select alpha in this case, such that that particular expression will become 0. That's what we want to satisfy our steady state air spec. If we simplify that a little bit, we can see that one of those z minus 1 factors in the denominator, due to the ramp input, gets canceled by the preceding z minus 1 factor in the final value theorem expression. We're left with the limit as z goes to 1 of 1 minus T sub C of z, Tz, T again is our sample period, we already know what that is, over z minus 1, but we realize that our steady state air due to a constant is actually going to impose that the limit as z goes to 1 of 1 minus T sub C of z, that's actually going to be 0. And because of that, we now have 0 over 0 in that expression for our ramp's steady state air. If we apply L'Hopital's rule, we can differentiate the numerator, differentiate the denominator, and look at those separately as the limit as z goes to 1. The t, the capital T, is our sample period. That's a constant. That pulls out of the derivative. And when we differentiate 1 with respect to z, that's 0. That goes away. And so really we just have a minus sign and t that we can factor out of the limit and the derivative. And upstairs we have the derivative of our desired transfer function, T sub C of z, with respect to z. Downstairs, if we differentiate the factor z minus 1 with respect to z, we just get 1, and the limit as z goes to 1 downstairs is just going to be 1. Remember what we had for our transfer function, T sub C of z. That's the desired. We haven't yet specified what k might be and what alpha is, but now we might be in a better position to see if we can now force this expression to equal 0 by the choice of k or alpha. In fact, it's going to be alpha that we will find is the variable that will force our ramp steady state air to be 0. Now, I could differentiate that manually, but I thought it might be sort of fun to do that with the calculator. So let's see if we can now differentiate that with the calculator. Let me see if I can find what I want. Now I want to actually do a shift minus. That gives me my differentiation expression rather quickly. I now want to differentiate with respect to z, and I now can put in this T sub C equation. Let me just say that that's now a k times, well, let me go ahead and put this all in a numerator. Let's say that's k times the expression z minus a. I'm not going to put in an alpha. And now what I want to do is divide that by the denominator, which is z squared minus 1.8162 I'm trying to find this expression in my notes, plus 0.833, and now I'll let the calculator do that differentiation, and I now see that I have the derivative of that capital T sub c of z with respect to z. Now what I want to do is actually look at that as, well, I'm setting that equal to 0 and trying to solve for k, or a. K is actually preceding everything, and I can then get rid of the k, or I can divide it out. I can divide out the minus sign as the limit as the denominator. Well, the denominator as z goes to 1 is going to be a constant, and so I can multiply both sides through by that. Let me just go ahead and sort of get rid of that and replace it with a 1. This is now my expression, or getting close to that expression. I'm going to go ahead and divide out by just deleting the k, or the minus k, and now I have an equation that I'm looking more like what I want. I want to look at the limit as z goes to 1, so let me just evaluate that vertical line, z equal to 1. I can now evaluate that expression when z goes to 1. I can now, if I can find what I want, I can now go up here and get the solve formula or function within the calculator, pull in the wave, or the expression that I want to equal 0, and solve that for a, and now I have found my a in my desired transfer function, capital T sub c of z, that's going to provide me with a steady state error of 0 due to a unit ramp. And that now allows me to come back here and say that now from the calculator, or I guess I've now called it alpha, or earlier I called it alpha, is now this 0.908. Is that what I had? 0.9086 if I wanted to get a little bit more significant digits. Now I have my T sub c with only one unknown parameter, which is the gain k. And now I have to be able to write down the correct values for these equations. I can now solve for that k based on my steady state accuracy spec due to a constant, and I want T sub c at z equal to 1 to equal 1, which now says that I have k times 1 minus 0.908 over 1 minus 0.9081 squared plus 0.0920 squared, and I want all of that to equal 1. If you do the algebra, k ends up being the denominator expression evaluated. Multiplying that through on both sides, I end up with 0.01691 over the 1 minus 0.908, which ends up being 0.1838. And now I have my desired transfer function, T sub c of z, is the k, which is the 1838, z minus 0.908, and the denominator written in rectangular form to explicitly sort of indicate where those two complex poles are located. And now I can use that expression for my desired closed-loop transfer function to generate or create my controller transfer function. I now have the controller design equation that I can simply use. That's now 1 over the plant, g of z, scaled by t sub c of z over 1 minus t sub c of z. Let me go ahead and do an intermediate calculation of finding that term in the square brackets so that all of this doesn't just blend into a mess. But let's now look at an intermediate expression, which is the t sub c of z over 1 minus t sub c of z. And the denominators will be the same. I will then really just be looking at the numerator of the denominator of that expression. The numerator is now 0.1838 z minus the alpha 0.908. That would all be over that second order denominator, but now I'm canceling both of those, and I now pull that denominator, z minus 0.9081 squared plus 0.092 squared. Then that needs to be, or we need to then subtract from that the numerator of t sub c of z, which is this 0.1838 z minus 0.908. If you perform the algebra, you end up with nothing new upstairs. Downstairs, you end up with z squared minus 2z plus 1, and that maybe looks very familiar. That's now just z minus 1 squared. That now is a simpler expression to deal with when we're scaling 1 over the plant by this t sub c over 1 minus t sub c. Doing that, c of z is now 1 over the plant, and our plant was this 1987 gain, z plus 0.9934 all over z minus 1, z minus 0.9802, all scaled by what we just derived. And now this, one of those factors of z minus 1 gets canceled. The denominator of our controller now is impacted by the numerator of our plant, which, and we'll take that 0.001987, or we'll multiply through by a 1 that will sort of clean that up. So I'll divide everything by the 0.001987, which is the 0.1838 divided by that, and we end up with then c of z equaling 925 z minus 0.9802. That's coming up from the pole of our original plant, z minus 0.908. And then downstairs we have one of those z minus 1 factors, and we have the z plus 0.9934. That's now our controller in this design method by Ragazzini. Let's go ahead and go back to MATLAB and see if we can simulate these results. So moving into MATLAB, we now have our plant. We now need to introduce the controller, which is also a transfer function, a discrete time transfer function. It's now 925 times, and now I don't want to just go ahead and try to multiply those manually, those two factors in the numerator. I'll just use the convolve function in MATLAB, and that will do it for me. I have z minus 0.908. That's one of the two factors in the numerator, and I have z minus 0.9802. Whoops. That's now my, that's my convolution to get my numerator. I now need to convolve to get my denominator. I now convolve the two waveforms downstairs, which is z minus 1 and z plus 0.9934. That's my convolution to obtain the denominator polynomial. And again, this is with a sample period of 20 milliseconds, or 0.02. There is now my controller transfer function. I now need to find my closed loop transfer function. I have C that I just created. I had G from before. And now what I want to do is I want to find this transfer function between the reference input and the output, which should be the t sub c of z that I already had. But MATLAB allows us to do that pretty easily. But first what I want to do is I want to form the product of the controller C and the discrete time plant G sub D, and I'll go ahead and display that. Then what I want to do is I want to build up the transfer function. I'll just call that capital T sub C, and I now need to combine in a feedback configuration that forward loop gain, that's what I just called L gain, and a transfer function with a unity transfer function, which is 1, and this is now my closed loop transfer function. If I look at the zeros of TC, and if I look at the pole of TC, now what am I missing here? Now what I want to do is I want to evaluate or examine the step response of that particular transfer function. So now if I look at the step response of that transfer function, if we look at that response, that's an unstable response, and so I closed up the recording session to try to find my error, and I had to go back into the MATLAB, and I noticed that my controller transfer function actually was incorrectly entered. I missed a comma in my controller transfer function, so let me go back and try to put that in and correct that. If I go back to the C, and here is now where I missed my comma to separate the Z and the minus 0.98, so hopefully that's now a correct controller. Let me now produce the loop gain with that new controller, and I believe that's looking a little bit better. Now let me create my transfer function with the proper forward gain in my system, and I can now look at the poles of that system, and those are looking pretty good, because if I look now at the zeros of those, MATLAB actually didn't cancel explicitly some of those zeros and poles in T sub C of Z, but if you do that, then you end up with the appropriate poles and zeros that we need. And now we're in a position, I hope, to find a better looking step response to our system. And there is a more acceptable looking step response. What we want to do, though, is actually examine the input waveform to see if everything is okay. Now that we've corrected the controller entry and put it in properly, let's now go back and say, that may well be good, but what's happening right here to our input? And we're really sort of saying, we're checking our work, we're saying, is everything okay? And one first place to look is to, let's look at the input command. That's actually driving the motor. Which really says that we are looking at this transfer function between the reference input R and the input U, as indicated here. But look at how we can actually re-sketch that. Maybe it's a little bit unclear because of all this other information around that. But now if we simply look at redrawing that block diagram, it might look like something that we're more familiar with. If we now consider this to be the signal of interest, that's our input signal, but we really haven't changed the interconnection structure whatsoever. We just sort of re-warped the figure so that now we can say, oh, the transfer function between the reference input R and the input U, again, this is just our Y right there, but we're interested now between R and U. We can find that. We can say that the transfer function between R and U is just the forward path transfer function, which is, in this case, our controller, C, divided by 1 plus the forward path, which is C, times the feedback path, which is G in this particular re-sketched block diagram, which says that the transfer function between the reference input R and the input U is now C of Z over 1 plus G of Z, C of Z. And we can actually have MATLAB do that for us. Let's now look at the closed loop transfer function that will give us U, and that will now be a feedback function in MATLAB where the forward gain is our controller and the transfer function in the feedback path is our discrete system G of D. So this is now our forward transfer function. This is now our transfer function in the feedback path. And then we'll simply do a step on our closed loop transfer function that created U. So if we do that in MATLAB, if I can now issue the commands properly, now what I want to do is, I was calling that a closed loop transfer function for U, is now the feedback command of our controller and the discrete system in the feedback path. If I now create a new figure and say, let's look at the step response of the closed loop transfer function for U, now we end up with maybe something that we had seen in class last time, and ooh, that does not look very nice, does it? So now let's examine that as to what it might be doing to our system in between the sample periods. And we could look at this maybe a little bit different. We could say, well, let me go ahead and do this in another figure window so that I can retain that one for other purposes. But now that should be in figure 4. We can now go back and say, let's just look at the axis of that from here. We give our x variables. Let's say we're looking at maybe from 0 to 2. And our y expressions, let's say that's going to go from minus 1,000 to 1,000. And now that's what our input is doing as a function of time. And we've spread out the horizontal axis. Now what I want to do, though, is I want to drive our system with this particular waveform, but yet look at the system response, which is really a continuous time system driven by this waveform. What I'm trying to say is we are actually now in between samples. If we wanted to think about it, from our original block diagram, here is what we have in the G of Z and C of Z configuration. What I'm going to effectively do now is I'm effectively going to take this signal U and use that to drive our analog plant so that we can now see what's happening between samples, because we're not seeing that here in Y of Z. If we go back to our output, that's not looking too bad, but we're actually just seeing the discrete time simulation. We're not seeing what might be happening in between each of those sample periods when we're exciting our system with some input that's so violent as to have this kind of behavior. So let me now do a little sort of funny business, and I'll maybe be able to explain that at a later time, or maybe as a sidebar. So let's now look at our input. We now have, or our time trajectory. Let's say we're creating our time vector from 0 to, with a sample period of 20 milliseconds, and we want to do that out to 16 seconds. Now let's build, or actually create, the input waveform that results from that time response. But now what I want to do is I want to actually sample that time axis on a much finer scale so that I can use that finer resolved time input response to drive my continuous system G. So to do that, what I'm going to do is I'm actually going to pad or introduce or duplicate the behavior of each of those input waveform signals. I'm going to create 10 in between each of those different steps. So now what I'm doing is I'm actually creating of length 10 for each input value. I've now created 10 copies of the same thing. And now what I want to do is I want to stack all of those up in one particular column. And now I will create a time vector that is also consistent with what I just created for my input. So I need to divide the sample period by a multiple of 10. Let me now find how many points I have in tFind, and let me look at how many points I have in uInput. Those need to be the same or my MATLAB function will not cooperate. So I need to cut off the tail of my input to give it 8,001 points. So I'm going to do that by saying take 1 to 8,001 for my input. So now what I'm doing is I'm cutting off and that's not really going to impact what I'm going to be seeing. So that now I can generate a new figure and I'm going to plot tFind with the uInput, and that should be just to convince myself that I'm plotting what I thought I needed to be plotting. And that looks like what I expected. That's my tInput. Now what I want to do is I want to look at the inner sample behavior, and I'm just going to call that y sample is equal to, and now I'm using a function called linear simulation of the continuous time system G with the input that I just created over a time horizon with the finer sampled waveform. And there is now my response with the inner sample ripple. Maybe it's not very clear what that looks like, so let me go ahead and resolve or get into a closer inspection of that. I'm now going between, let's say, 0 and 1.4 in my output response. So I'm now going to isolate on a smaller time window. And that's now my inner sample ripple behavior that I had. And I could look at the input waveform also and examine that behavior, but we've already sort of seen what that does. So that's now what's happening to our system because of what? So now what we need to figure out is what actually is happening. We maybe didn't expect that from our step response of the output, but we actually have a violent input trajectory, or the violent input trajectory is a result of the pole at this negative value of minus 0.9934 in C of Z. And if we go back into our, did we find the pole of our controller? Maybe we didn't. But if I now look at the pole of C, you can see that we have one pole at Z equal 1 and another pole at minus 0.9934, and that's on the negative real axis, and that causes this violent switching to happen in our input. So the original discrete time simulation of the step response was actually a little bit misleading. By that, I'm meaning that particular response. That one doesn't look too bad. And what we were missing was we were missing the violent behavior in our input trajectory or waveform, the violent input trajectory actually causes this intersample ripple. And the reason that that's occurring, I'm going to try to make this as a note, in a sample data system, which is really what we're doing. In a sample data system, the system, the G of S, really only sees the input as a constant between sample points. It's not constantly feeding back an output and using that to instantaneously adjust the input. The input is sort of fixed at each sample period, and because of that, in a sample data system, the system is in an open loop operating mode, or in an open loop mode, between the changing input values. And so what we were doing, or what we did do, is we actually were driving the open loop system G of S. That's what I was trying to show here in this block diagram configuration. We were driving this open loop system G of S with the input waveform to see the intersample ripple. what I would like you to sort of take away, or the lessons that we've learned from this example or this excursion into the direct design method of Ragazzini, is sort of the following. We've learned that the controller needs to be causal, which means we can't remove the natural delay from the original system. We definitely do not want we would like to avoid controller poles on the negative real axis. Let's say the ones that might cause this violent switching behavior. Those are undesirable. And those we're saying are maybe between z equal minus 1/2 to z equal minus 1. We don't want the controller, C of z, to be canceling any unstable poles or zeros. That will cause internal instability in our system. The zeros in T sub C of z, if we go back and look at our step response here, that actually didn't meet the 5% overshoot behavior that we wanted, and one of the reasons for that is because our closed loop transfer function, T sub C of z, actually had a 0. Did I have that anywhere in MATLAB? Let's see if I can find. We have a 0 at 0.908. That was the 0 that we used to fix our steady state air spec, but that 0 at a real value in the example that's pretty close to z equal 1, and that now sort of negatively impacts the percent overshoot behavior. Now, if we wanted to try to eliminate that pole in our controller at minus 0.9983, we could have included that as a term in our direct design formula for T sub C of z, but that's going to make C of z more complicated, and because of that, maybe we want to look at other design approaches before we continuing to modify T sub C of z. So if we modify T sub C of z to maybe reduce some of the poor behavior that's caused by that pole that occurred in our controller, C of z, at the negative 0.9934, that's just going to make our C of z more complicated. We also want to examine the input waveform when we're doing any of these designs and make sure that it doesn't exceed the physical limits of the system. In our particular case, it was now banging back and forth between plus and minus 1,000 and violently going back and forth between those values for a long time into the response trajectory, and we may not see that in our trajectory unless we look at the inner sample ripple, but even there we're not seeing this very large value for the input magnitude. And that large value is probably going to saturate our system, and if we then hit the saturation limits, we're not going to be exciting our system with a magnitude of 1,000, but maybe a magnitude of 10, and that's not going to get us to the location that we were expecting to get, and that's going to make our response much more slow than what we were expecting. And we also probably want to examine the input waveform and see, is that input fluctuating wildly between plus and minus values? And if it is, we probably don't want to continue down that path with our controller design. That's where I would like to stop this particular discussion of the direct design approach or method of Ragazzini applied to a normalized DC motor.